For decades, our entire digital world has been protected by math problems, problems that are just incredibly hard for regular computers to solve. But what happens when a totally new kind of computer shows up, one that can crack those problems like they're nothing? Well, that's the threat of quantum computing, and it's forcing all of us to ask a really big question. What on earth do we do next?
And that brings us to maybe the single most important question in cybersecurity right now. Seriously, if these quantum computers can just shatter the encryption we use for everything, I'm talking about stuff like RSA, what's left? Is there any kind of math out there that's still hard enough to build our new digital fortress on? Now, you'd probably think the answer would come from the same old playbook, something to do with really complicated number theory. But the real answer? It's something else entirely, something you probably didn't see coming. It's all about geometry.
Yeah, you heard that right, geometry. And that leads us straight to the star of today's show, the lattice. So what is this thing? And how can something that basically sounds like a garden fence be the key to our entire quantum-safe future? Okay, so what exactly is a lattice? Well, at its heart, it's just a grid. Think of a perfectly regular pattern of points stretching out forever in all directions. You could almost picture the atoms in a perfect crystal, all lined up. That's the kind of structure we're talking about, but as a pure mathematical idea. Let's start simple, in 2 dimensions, just to get a feel for it. Here, a lattice is nothing more than the grid you'd see on a piece of graph paper. It's super easy to see every point and its neighbor. Everything is nice and orderly, totally predictable. But here's where it gets interesting. The real magic of lattices isn't in our familiar 2D or 3D world. See, mathematically, these grids can have hundreds or even thousands of dimensions. And it's when you go into that crazy high-dimensional space that our simple little grid becomes this almost unbreakable fortress. So that's the million-dollar question, right? Why are they so secure? What is it about these high-dimensional grids that makes them so incredibly tough to crack? And I know what you're probably thinking. Hang on, if it's just geometry, can't we just, I don't know, draw a picture and figure it out? And you know what? That is a perfectly logical question. It feels like we should be able to just see the answer. And back in our simple 2-dimensional world, you'd be 100% right. If I just drop a random point anywhere on this 2D grid and ask you to find the closest lattice point, well, it's a piece of cake. You can literally just see it. There's no challenge there at all. But the second we jump into hundreds of dimensions, our brains just break. Our intuition completely shatters. That simple little task of finding the closest point, it becomes nearly impossible. The complexity just explodes into this massive mathematical labyrinth, and even our best supercomputers get totally lost trying to find their way through it. And this right here is the absolute key. The experts are all pretty much in agreement. These lattice problems seem to stay hard even for a quantum computer. That geometric hardness is what gives them their power. It's what makes them resistant to the very kinds of attacks that could bring our current systems to their knees. So let's just put this side by side to make it super clear. The old guard, RSA encryption, that's all about number theory. Its hard problem is factoring gigantic numbers. Lattice-based crypto, it's a whole new game. We've shifted from number theory to geometry. The new hard problem is all about finding that one closest point in a dizzyingly complex high-dimensional lattice. Okay, so we've established they're incredibly tough to break, but that's only part of the reason everyone's so excited. What are the practical upsides? Why are researchers and governments all betting on this specific approach for our future? Well, it really comes down to a killer combo. First, and most importantly, they're believed to be quantum resistant, which is the whole point. But second, they're also surprisingly efficient. You can build really fast algorithms with them. And third, because they're both secure and fast, they've become the top choice for the folks who write the official new standards for cryptography. And listen, this isn't just some far-off academic theory. Lattices are being put to work right now. They're paving the road to a new global standard that's going to protect all of our data. And if you want proof, look no further than the U.S. National Institute of Standards and Technology. That's NIST. They ran this huge, multi-year global competition to find the best quantum-proof algorithms out there. And after years of the world's best cryptographers trying to break everything, you know what they chose? Algorithms based on lattices. This transition is happening as we speak. Now, just to be clear, we've definitely been flying at 30,000 feet here. We skipped all the nitty-gritty vector and matrix math. We didn't dive into specific algorithms like Krystal's Kyber. The goal today was just to give you a solid gut feeling for the main idea, this shift to geometry. So, as we start to land this thing, what's the bottom line? If you're going to remember just a few things from all this, what should they be? Here's the whole story in a nutshell. Lattices start out as simple, regular grids. But when you take them into super high dimensions, finding your way around becomes an incredibly hard problem. That hardness is what makes them so tough that even quantum computers can't seem to crack them. And because of all that, they're now officially the foundation for our next generation of digital security. So we've talked about the what and the why. The next obvious question is how? How do you actually use this idea to protect an email? In our next explainer, we're going to tear down one of the actual algorithms that won that NIST competition and see how these geometric ideas are really put to work. You won't want to miss it.